Today, we are about to study an interesting topic which lies under the broad umbrella of physical spectroscopy. Today, our major focus will be on studying an interesting spectroscopy which is also known as rotational spectroscopy. Okay, now what exactly is rotational spectroscopy? To understand rotational spectroscopy, we apply this specific kind of spectroscopy on particular molecules. Why do we apply rotational spectroscopy on particular molecules? In order to determine, what do we determine using rotational spectroscopy? Precise molecular arrangement. Precise molecular arrangement of atoms slash entities which forms the molecule. Basically, we talk about bond lengths and bond angles using rotational spectroscopy. Now, understanding the word spectroscopy, what do we know? Spectroscopy is actually what interaction of light with what your matter, and the outcome of this interaction is studied and it generates an spectra, and therefore it is called as spectroscopy. Now when the particular change in the matter is occurred in the rotational aspect of the molecule, we coin that term as rotational spectroscopy. Well, fair enough? Yeah. Now, since we just studied that, spectroscopy is interaction of light or electromagnetic radiation with matter. It also matters what kind of your radiation is interacting with the matter. In case of rotational spectroscopy, we observe that electromagnetic radiation which is being used is what? It is your microwave radiation. Okay, it is microwave radiation, and therefore we can also call the rotational spectroscopy as microwave spectroscopy. Now, before proceeding into the further aspects of rotational spectroscopy, there is a point which I would like to put forward. Like, it is very important, as we will be studying the upcoming parts of the physical spectroscopy followed by this current topic, that is your rotational spectroscopy. We will definitely need this point in our minds, and therefore I would like to put forward that is your the spectroscopy, the energy wise, how the radiation changes and under what broad category does it falls, and like, yeah, so basically I would try to explain how is the energy varying when the particular kind of radiation is being used. Okay, starting from the one with the least amount of energy, we have radio waves. We have radio waves. Now, followed by radio waves, we have microwaves. Followed by microwaves, we have IR rays. Followed by them, we have UV rays. Followed by UV rays, we have X rays. Followed by X rays, we have gamma rays. Okay, yeah. Now, let's try to write down the values of the frequencies associated with the radiation. Now, why are we even talking about frequency? We know that the energy of a particular electromagnetic radiation is given by the universal equation E is equal to h nu. Now, the nu in this equation stands for what? It stands for frequency. Now, depending upon the range of frequency, the energy range is figured out. Okay, So particularly if we try to speak about this series of radiations, every particular radiation, that could be radio wave, microwave, infrared ray, ultraviolet ray, x-rays or gamma ray, they fall under the certain category or fall under the certain boundaries of energy. Now those energy levels can be studied if we know the frequency range of this particular radiation. Speaking about radio waves, the range of frequency is 10 raised to power 6 to 10 raised to power 8 hertz. Okay, yeah. Microwaves fall into the category of 10 raised to power 10 to 10 raised to power 12 hertz. Infrared radiations fall under the category of 10 raised to power 10, 12 to 10 raised to power 14 hertz. UV fall under the category of 10 raised to power 16 to 10 raised to power 18 hertz. X-ray fall under the category of 10 raised to power 18 to 10 raised to power 20 hertz. And the gamma rays fall under the category of 10 raised to power 20 to 10 raised to power 22 hertz. Now we just saw the equation of energy, that is E is equal to h nu. As the value of your frequency, this will increase, the energy tends to increase. Okay, why? Because there is a direct proportionality between energy and the frequency. Now if we see to the values of the frequency in this particular series, we see that the energy tends to increase as we move from left to right. Okay, the energy tends to increase as we move from left to right. Isn't that true? Yes. Now let us try and understand the next aspect of this particular series. Now see what exactly is happening when you are studying nuclear magnetic resonance spectroscopy, that is NMR spectroscopy, which we usually study for organic molecules. We there use radio waves which fall in this category, that is 10 raised to power 6 to 10 raised to power 8 hertz. What kind of transitions do we observe there? There are nuclear transitions associated with. So we have nuclear transitions. The spin state of the nucleus changes when you apply a particular radio frequency which matches that of your resonant frequency. This particular transition is observed. True? Yeah. Now, if we try to analyze the next part, that is your microwaves. These microwaves are responsible for rotational transition, and thus we call the spectroscopy under the microwave as rotational spectroscopy. This is responsible for rotational transitions. Your IR is associated with vibrational transition, while your UV is associated with electronic transitions. Okay, yes, associated with electronic transitions. Now let us try to figure out certain more details of this particular series. Okay, now let us try to write all these parts. Let's just copy paste this part, copy, and we just wanted to paste it here. Yeah, paste it. Okay, yeah. So now let us try to check what kind of transitions are possible when we apply a particular kind of radiation. If we apply, see, if we apply microwave, microwave radiation are responsible for rotational transition, so they will show it, but energy of that of your microwave radiation is not sufficient in order to carry out vibrational transitions, and therefore vibrational transitions will not be observed. Similarly, electronic transitions will also not take place. Why? Because it requires much higher energy as compared to that of rotational transition, and the amount of energy required for electronic transition is not being able to be fulfilled by using microwave radiation. So electronic transitions are also out of this picture. Okay, yeah. Secondly, if we apply IR radiation, now since your IR radiation is of higher energy as compared to microwave radiation, we can now still observe our rotational transitions along with our vibrational transitions, but the energy is still not sufficient in order to carry out the electronic transition. So electronic transitions will not be observed in this case. But if we use ultraviolet radiation, what in this case, since the energy is sufficient to carry out all of the three transitions, we can observe that UV rays can be used to carry out rotational transitions, vibrational transitions, as well as electronic transitions. And this is very much important. Why? This is actually clearly seen when you try to actually study your vibrational spectroscopy or Raman spectroscopy for that case. Okay, so we'll see why we can observe that actually rotational and vibrational transition takes place when we try to study our IR or vibrational spectroscopy, which is also part of our syllabus. Okay, yeah. Okay, now this is actually kind of very important point. Okay, so now our core focus for today's session lies in rotational spectroscopy. Now, for a particular molecule which we are trying to study under the rotational spectroscopy must follow a prerequisite condition. And what is the prerequisite condition? The prerequisite condition is that the molecule must possess permanent dipole moment. Okay, permanent dipole moment. That means the molecule should be polar. Okay, पोलर तो होना चाहिए, उसके साथ उसमें परमानेंट डाइपोल मोमेंट भी होना चाहिए. A molecule can be polar if there are certain atoms of variable electronegativity present around themselves, but it also has to be organized in such a way that it possesses a permanent dipole moment and not a dynamic dipole moment. What is a dynamic dipole moment? A dynamic dipole moment is the kind of dipole moment which only arises due to certain type of asymmetric modes of vibration. Okay, if that is not the case, and if your molecule in its natural state shows dipole moment, we call such molecule to possess permanent dipole moment. Okay, yeah. So if the molecule possesses permanent dipole moment, we can say that this particular molecule is actually rotational spectroscopy active. Okay, so we call such molecules as rotational active molecules. Okay, rotational active molecules. Yes. Now, if we are trying to study rotational spectroscopy, we are actually studying what? Rotational transitions. Now, these rotational transitions have to take place between what? Rotational energy levels. So, for sure, we will now be having rotational energy levels across which the rotational transitions will take place. Okay, so we have some rotational energy levels. Now, we have an Bohr's frequency rule which is useful in order to figure out how is the energy of this particular energy level can be determined. Okay, so the Bohr's frequency condition states that, what is the Bohr's frequency condition states? Bohr's frequency condition Bohr's frequency condition states that the energy of the rotational level E j is given as beta j into j plus 1. Now, what is the significance of each particular term in this particular equation? The B stands for rotational constant. Okay, it is the rotational constant. What does the J stand for? J stands for rotational quantum number. Okay, rotational quantum number. Quantum number. Based on variation in the rotational quantum numbers, we get energy levels which are also coined as your rotational energy levels. Okay, yeah. So these two particular points are important, and this Bohr's frequency condition is very much mandatory for studying the energy levels and to figure out what is the energy or what is the magnitude of those energy levels. Okay, so beta is rotational constant and J is the rotational quantum number. Okay, now what is the baseline condition? The baseline condition is that J, that is your rotational quantum number, it can actually start from 0, 1, 2, 3 and so on. So basically J belongs to this set of whole numbers. Okay, yeah. So if I try to start denoting the level or try to figure out what is the level of a particular rotational energy level, for that the ground state will be at a particular energy level where the rotational quantum number becomes 0, followed by it increases J equal to 1, this energy level J equal to 2, this energy level depicts J equals to 3, this energy level depicts J equals to 4, yeah, and just so on. It just goes on. Okay, if I go and substitute the values of this particular energy rotational quantum numbers into the energy of the Bohr's frequency condition, I get the energy of those particular levels. Okay, so when the value of J is equal to 0, your EJ becomes what? 0. So your ground state, this is what? This is your ground state. You need a page. Yeah, what is this? This is the ground state. Okay, this is the ground state energy level. Then we have E1, which is what? It is beta into 2. It is basically 2 beta. Okay, then what will be if it is J equals to 2, E2 is equal to beta into 2 into 3, so it will be what? 6 beta. Yeah, what will be E is equal to 3, so it will be beta into 3 into 3 plus 1 is 4. True, 3 plus 1 is 4. Yeah, 4 3s are 12 beta. Okay, yeah, and it just goes on. Okay, it just goes on. Yeah, that is how it works. That are the energy, this is the value or this is the magnitude of that of your rotational energy levels, along which we can actually observe the rotational transition when a particular microwave which has a frequency resonant to that of the quantized energy levels in this particular rotational levels, we can observe rotational transitions. Okay, yeah. Now this transitions, okay, now this particular transitions, that is the process of excitation and relaxation, emits a particular kind of light or particular kind of radiation, and this radiation is captured by the detector and it generates an spectra. Okay, now the generated spectra, okay, now this particular generated spectra shows you spectral lines. Now when it shows you spectral lines, the spectral lines are of variable intensities. Okay, the spectral lines of our various intensities. Okay, but the spectral lines are always what? They're always separated by a constant distance, that is the splitting between the spectral lines is always constant, and that is 2 beta. This is a common question which is usually asked in examinations. So the splitting between them is always the same. Maybe the spectral lines which are being splitted by 2 beta are of different energies. Why? Because we just saw that the energy levels of that of your rotational energy levels is not following any kind of, like, they are not, the difference between the energy levels is not same. Like if we see for the transition of J equal to 0 to J equal to 1, the energy associated with that transition is different as compared to when it is from J equal to 1 to J equal to 2, J equal to 2 to J equal to 3. So it is for sure that the energy difference between two particular energy levels or rotational energy levels is not the same. But so what does it mean? That the intensities are different. But even if the intensities are different, when we record a spectra for a rotational spectroscopy, there are various spectral lines which are associated with this particular transitions of different energies. But those spectral lines are always separated by a distance of 2 beta, and that is what is of our concern. Okay, yeah. Now, see, now what is exactly happening in this case? See, now let us try to figure out what kind of energy difference I can observe. Okay, now let us understand. You are going for a particular transition where you are having your rotational quantum number as J, it has moved to an rotational quantum energy level with rotational quantum number j plus 1. Why only j plus 1? Because, see, there is a selection rule for a particular when you study rotational spectroscopy. That means only those transitions are valid when the delta j turns out to be plus or minus 1. Only those transitions are allowed or valid when delta j is equal to plus or minus 1. That means the transition can either be from j to j plus 1 or from j plus 1 to j. That's it. So for this particular transition, let us try to figure out what would be the difference in the energy levels. Okay, so let us try to write it as delta E. What will be the delta E become? Let us try that higher to lower we are doing. So E of j plus 1 minus E of j. Yeah, basic equation mathematics. Yeah, so E j plus 1 क्या हो जाएगा? It will be beta into j plus 1 into j plus 2. True? Minus beta into j plus 1. Now what is it? Just solve the mathematics, and if we solve this equation we get 2 beta into j plus 1 as the energy difference for a particular transition. This is going to be constant. Okay, now whatever the amount of energy, whatever energy levels you consider, if we consider transition from j equals to 3 to j equals to 4, for this also this equation is valid for 4 to 5, 5 to 6, 6 to 7. For any rotational levels, the difference between two conjugative energy levels of a rotational transition for rotational transitions will always satisfy this particular equation. Why? Because the selection rule for rotational spectroscopy says that the difference in the rotational quantum number for allowed transition has to be plus or minus 1. Okay? Yeah. So this is what is only giving you allowed particular transitions. Yes. Now, let us understand what is exactly your B compromised of. Okay? What is B? Or B or beta? What is beta? Beta we just spoke about. It is the rotational constant. Okay? It's a rotational constant. Okay. Now this particular rotational constant is given, or it can be expressed as beta is equal to h square over 8 pi square I. Okay, this is how you actually figure out the value of your beta. So if you know the value of Planck's constant, you know the value of your moment of inertia, you are ready to go and you can just put the values in this equation and you can get the value of your rotational constant for the particular molecule. Okay, so now let us try to figure out some relationship out of this equation. Okay, now what is the unit for a rotational constant? If it is written in this form, it will give me my data in joules. Okay, but if I have to figure out the value of your beta in centimeter inverse, okay, in centimeter inverse, or if I have to figure out it in centimeter second inverse and in centimeter inverse. For second inverse, we can write the same equation. Beta becomes equal to h by 8 pi square I. While if I have to get it in centimeter inverse, I will just multiply the moment of inertia by the speed of light in centimeter per seconds. Okay, yeah. So beta becomes h by 8 pi square IC. Yeah. So if I have this particular equations, I can just figure out the value of rotational constant either in joules, either in second inverse, or either in centimeter inverse in all of the three above unitary methods. Okay, yeah. So this is one more important point to be added in our particular bunch of formulas in order to study and understand the core of this spectroscopy. Okay, yeah. This was an very interesting and good point. Now, see, what does this says? Beta is equal to what? H square by 8 pi square I. Looking to this particular equation, what can I say? That h square by 8 pi square, this all the terms are constant. Yes. So the only term which is affecting your beta is your I. That is, a rotational constant is only and only influenced by moment of inertia. How do you calculate moment of inertia? Moment of inertia can be calculated as mr square. Yeah, we studied in the rotational motion, class 11 physics. Yeah, so moment of inertia can be studied by mr square. Now since we are particularly studying, see, we are particularly studying rotational spectroscopy for diatomic molecules, we need to get the reduced mass of those particular molecules. Why? Because direct masses are of no use to us. So because they are actually merged into each other, there is certain kind of overlapping. So what do we try to figure out, or what do we try to take the middle way in order to make our work easy? What we do is we figure out their reduced mass, and from the calculations of the reduced mass we can see a lot of things about the rotational spectroscopy. Okay, see, okay, so I is written as, so we can write for the particular diatomic molecule it becomes mu r square. Okay, r is the radius. या डायटोमिक मॉलिक्यूल का जो रेडियस होगा वो रेडियस वैसे के वैसे रखेंगे. अब यहाँ पे आ गया तुम्हारा रिड्यूस्ड मास. व्हाट इज म्यू? म्यू इज रिड्यूस्ड मास. ओके, म्यू इज reduced mass. How is reduced mass calculated? Reduced mass is calculated as m1 m2 over m1 plus m2. Okay, m1 m2 over m1 plus m2 is your reduced mass. Okay, this is the formula for the reduced mass. Okay, now what exactly happens is, usually what do we observe? We observe questions associated with the isotope substitution. Yeah, like if we try to study HCl molecule. Okay, if we try to study HCl molecule and we compare it with DCl, that is deuterated chloride, this hydrochloride, that is deuterated chloride. Okay, yeah, so the mass number is 1 for hydrogen, mass number is 2 for the deuterium. Okay, yeah, so now this entirely changes what it entirely changes your reduced mass. See, due to incorporation of deuterium instead of hydrogen, what exactly happens? The reduced mass tends to increase. Okay, see, beta is beta is directly proportional to I, inversely proportional to I, we can say that. So beta is actually inversely proportional to mu. Okay, yeah, so yeah, if the mu increases, beta has to decrease. Okay, yeah, and if beta has to decrease, which also says that the energy decreases. Very true. Why? Because energy is what? Energy is beta into j plus 1. J into j plus 1 remains constant. So if the beta drops down, energy drops down. So if we do isotopic substitution with a heavy isotope, what exactly happens? Reduced mass drops, reduced mass increases, and if the reduced mass increases, the rotational constant drops, and if the rotational constant drops, the energy value also drops. Okay, yeah, very straightforward. Yeah, so this is what you should know while studying and understanding, while studying and keeping in mind certain point sets while you actually perform rotational spectroscopy in a laboratory and try to interrupt your data. Yeah, okay, now there is one more kind of term associated with this kind of spectroscopy, and that is associated with the population levels of your population level of your particular spectrum. See what exactly is happening. What is actually transitions? That means there are certain molecules in the ground state or in a particular energy state. They are free or they are certainly energized, but they are in their most stable state. Okay, what exactly happens when you irradiate those molecules, or when you make a particular light or a radiation interact with them? You are basically perturbing their natural existence, or you are basically disturbing them by providing certain amount of energy, and when they absorb this certain amount of energy, they show transition. But when the transition occurs, what exactly happens? It is not their natural state. They are kind of unstable when they show transition and they move to a particular rotational energy level. Okay, yeah. So what exactly happens? They do not stay for a longer time in those excited states. They try to release of their energy and try to acquire a state which is quite stable, and therefore there is a transition which is followed by emission of a particular radiation, and that's how this entire concept of spectroscopy works. Okay, yeah. So what exactly is happening in this case now? Now since there is again drop down of your excited state to ground state, what exactly happens? The population keeps on hopping in the excited state, coming back to the ground state. So for that we must study what is the population ratio. Yeah, so population ratio is given by a very beautiful equation. Okay, is given by a very beautiful equation. We even studied this in statistical thermodynamics. The equation stands as Ni over Nj is equal to Gi by Gj into e raised to power minus of Ei minus Ej by kBt. What is kb? Kb is your Boltzmann constant, T is temperature. Gi by Gj are the degeneracy of that particular energy levels. Ni and Nj represents the number of molecule or the population. Okay, see Ni and Nj kya hai bhai? This is the population of atoms or population of your molecules or entities in that particular energy level. The energy level is ith energy level and jth energy level. Okay, I and j are the energy levels. Let us write this down. So ith and jth एनर्जी लेवल आहेत. ठीक है, एनर्जी लेवल्स. ठीक है, एंड एन आई एंड एन जे क्या हुए? दे आर द पॉपुलेशंस. एन आई एन जे आर population in those energy levels, population of those energy levels. Okay, yes, are the energy levels of those population levels. Now what is gi and gj? Gi and gj are degeneracy of those energy levels. What is degeneracy? That is also an interesting point. Degeneracy of those energy levels. Okay, this is the degeneracy of those energy levels. Now degeneration of energy levels is means how many energy levels of same energies are present in your rotational transition. Okay, now suppose we have a particular energy level which has energy of 3b. Okay, at 3b, or let us suppose it is 12b. So now how many energy levels of 12b are present is called as your degeneracy. So that is Gi by Gj. And in rotational spectroscopy, in order to study number of degeneracies is given by a very important formula. That is degeneracy is given by 2j plus 1. Okay, this 2j plus 1 will give you the number of degenerate states in a particular energy level of a particular energy level. Okay, this is given by 2j plus 1. Very important formula, must be remembered always. Okay, yeah. So this formula is overall very much beneficial in calculating the population ratio of the ith and jth energy level when you try to study your rotational transitions. Okay, yeah. Now, studying about this kind of data, we must also try to now classify the molecules. Na? In which category does this particular molecule fall under the rotational spectroscopy? So it becomes easier to just look at the molecule and figure out which particular kind of classification this molecule shows and what kind of result we can expect. For that, what we do is we study different types of rotors. Okay, so very firstly we have linear rotors. Okay, we'll study types of rotors. What is the first type of rotor? First is your linear rotor. Okay, what exactly happens in the linear rotor? See, now there are particularly 3 axes. Okay, what are those axes? X axis, y axis, z axis, 3 axes. Okay, so we have 3 axes along which we can actually figure out your moment of inertia. Okay, if the moment of inertia along one axis is 0, that is the internuclear axis. Okay, now for linear molecules such as HCl, okay, so this is its internuclear axis. Along this internuclear axis, the moment of inertia has to be 0. Why? Because there are no masses revolving around those axes, so the moment of inertia becomes 0 in such cases. So this I, let us consider this as IA is 0, and there are more two axes, which is this axis and this axis. Okay, so these are two axes more present in HCl molecule. Yeah, that could be named as IB, IC. So they are not 0. Okay, so IB and equal to IC, but they are not equal to 0. Okay, so this is the criteria for your linear rotors. Okay, now what is the second kind of rotor? A second kind of rotor is an asymmetric rotor. Okay, it is an asymmetric rotor. It is an asymmetric rotor. Okay, this asymmetric rotor is also kind of very interesting category. See, like if your particular molecule is not linear, okay, if it is not linear, secondly, if it has only C1 C2 point group, then we can call them, okay, if they belong to C1 C2 point group, then we can call them as asymmetric rotors. For example, we have water, which belongs to the category of asymmetric rotor. It has permanent dipole moment. It belongs to the point group of C2V. okay, या C1 एंड C2 के जो पॉइंट ग्रुप्स है उसको बिलोंग करने वाले जो मॉलिक्यूल्स होंगे जो परमानेंट डाइपोल मोमेंट शो करते हैं वो एसिमेट्रिक रोटर के कैटेगरी में फॉल करेंगे. ओके, या नाउ there is a third and one more interesting category of rotors, which is called as symmetric rotors. That is called as your symmetric rotors. हाँ, so symmetric rotors में अभी दो कैटेगरी आते हैं. तो सबसे पहले चले उनको मॉलिक्यूल्स को लेकर समझते हैं. ठीक है, इफ वी टेक मॉलिक्यूल ऑफ BF3. ओके, वी टेक मॉलिक्यूल ऑफ BF3. ये जो BF3 मॉलिक्यूल है इसमें क्या क्या प्रेजेंट है? पहली बात, इसमें प्रेजेंट है प्रिंसिपल एक्सिस कौन सा है इसमें प्रेजेंट? इज इट C3 और इज इट C2? Which is the axis? Is it C3? So we have C3 axis present as the principal axis. Then what do we have? We have perpendicular C2 axis also present in this particular molecule. Yes. So what exactly happens? There are two type of axis present. Okay, how many C2 axis are present? There are 3 C2 axis present. Okay, yeah, 3 C2 perpendicular axes are going to be present. Two types of axes. So what exactly happens if we try to rotate the molecule BF3 along the C3 axis? What exactly happens? How many atoms goes in motion, or how many atoms are actually showing rotation? So number of atoms rotated in the C3 axis are 3, and the number of, that is what when is the C2 passing? The C2 passes through what? It passes through one boron fluorine bond. This is your C2 axis. Okay, yeah. So when the C2 axis is used, is applied, what exactly happens? Only the fluorine atoms are revolving or rotating. So the number of rotations in C2 axis will be 2. So the more the number of atoms rotated along a particular axis, the higher will be its moment of inertia. So the moment of inertia along C3 will be more. See what exactly happens? There are always 3 axes. Okay, there are always 3 axes. So one is C. There are always 3 axes: IA, IB, and IC. Okay, IA shows minimum. Yeah, yeah. So there are 3 axes A, B, C. So IA, that is the moment of inertia which is minimum. Then along the axis B, your moment of inertia can either be minimum. Wait. Moment of inertia can either be minimum or maximum और entirely different as well. Okay, entirely different भी हो सकता है और entirely different हो सकता है, and IC is always the maximum. Okay, yeah. Now what is the case in this particular scenario for BF3 molecule? We have one particularly C3 axis which has highest amount of rotating atoms, so the IC will be along that of your C3 axis. So ठीक है, so we have IC which is greater. Then we have two axes IB, IA which are same. Minimum is along the C2 axis, and the middle wala, that is IB, is also same, which is also minimum, which is same to C2. So we have IA is equal to IB in this particular case. Yes, yes, and your IC is greater. Okay, so this particular case when the maximum moment of inertia जो होता है, ठीक है, मैक्सिमम मोमेंट ऑफ इनर्शिया जो होता है वो यूनिक है, ठीक है, दिस इज यूनिक. मैक्सिमम मोमेंट ऑफ इनर्शिया MOI इज यूनिक. उस पर्टिकुलर रोटर को हम बोलते हैं, उस पर्टिकुलर रोटर को हम बोलते हैं ऑब्लेट. ओके, दैट पर्टिकुलर रोटर इज कॉल्ड एज ऑब्लेट. ठीक है, यस, एंड उसके ऑपोजिट वाला होगा तो उसको क्या बोलेंगे? प्रोलेट. नाउ एक प्रोलेट का केस भी स्टडी कर ही लेते हैं. नाउ सपोज करो आपके पास एक मॉलिक्यूल है दैट इज सी, वी हैव आई बॉन्ड, वी हैव एच एच एच, CH3I. Okay, yeah. Now start figuring out how many axes do we observe in this particular molecule. We pass this is the internuclear axis. Okay, what is it supposed to be? It is supposed to be rotating how many atoms? Two atoms. Okay, so two atoms ये कर रहा है rotate. Okay, this and this is a perpendicular axis present. Along this particular axis कितना कर रहे हैं देखो, 1 2 3 4 5. इसके अलॉन्ग कितना आ रहा है? 5 हो रहा है. इसके अलॉन्ग भी कितना हो रहा है? 5 हो रहा है. ठीक है. सो नाउ व्हाट एग्जैक्टली इज हैपनिंग इन दिस पर्टिकुलर केस? व्हाट इज एग्जैक्टली हैपनिंग इन दिस पर्टिकुलर केस? सी, ये वाला है मिनिमम वाला, सो इट हैज़ टू बी IA, दिस हैज़ टू बी IC, दिस हैज़ टू बी IB. ओके, नाउ इन दिस केस व्हाट एग्जैक्टली हैपन्स इज द मिनिमम मोमेंट ऑफ इनर्शिया, मिनिमम मोमेंट ऑफ इनर्शिया जो है, मोमेंट ऑफ इनर्शिया इज यूनिक. ठीक है, यूनिक, वाइल मैक्सिमम moment of inertia is not unique, so how can we write it? We can write it that IC now becomes equal to IB, which is greater than IA. This shows that the lowest moment of inertia, minimum moment of inertia is unique. So this particular case of rotor is called as prolate. Okay, yeah. So as of now I think that is kind of all which is helpful in covering and understanding all the particular aspects of rotational spectroscopy. I would definitely love to bring up some problem solving session in the upcoming days, and we'll for sure solve some very interesting and intriguing questions and try to make hold on to these topics and make sure that we score well enough in the exams. And yeah, I know like we will definitely be at places we are going to definitely make it through this particular exams, particular life, and we are made for this thing, and I believe in myself, so I do think that you believe in yourself as well. That's enough of motivation for my side. Yeah, this is Pratham signing off. Yeah, take care, bye, thank you.